Thank you.
Good afternoon, everyone. Yeah, so just one second. Good afternoon, everyone. So welcome to the fourth FedEx IIT Madras seminar series, which is conducted under the aegis of the FedEx Center for Sustainable and Smart Supply Chains, the Smart and Sustainable Supply Chains. Today we have our alumnus, Goda Doreswamy, right, who is the VP of Data Science or Data Analytics at Swiggy. And we look forward to a talk on applications of optimization, right? I guess Professor Rajendran, who was the one who introduced her and recommended her as a speaker for this series, I request him to say a few words inviting Goda before she can start. Professor Rajendran, over to you.
Sir, you are on mute. Professor CR, you are on mute.
I'm extremely sorry. Thank you.
Yes.
I'm very happy to introduce Goda to all of you. She was my student in the course on computer simulation. She did her integrated MTech program in biotechnology. And she was a silver medalist, if I'm right. So she was a brilliant student. And no wonder, I'm really happy that she took to optimization as a career, switched over from biotech to industry engineering and operations research. So doing great. I'm so happy to see Goda, and I'm also happy to stay in touch with her. And as a student, she was extremely studious. So at the end of every class, almost she used to come up with many questions, which I found really interesting to answer. So really happy to stay in touch, and also it's more like a daughter to me. Thank you.
Thank you, sir. So kind words.
Thank you, sir. Thank you, Goda. Over to you. Thank you, sir. Goda, over to you. So the whole floor is yours. Thank you very much.
Sure. Thank you. Just before I start, like sir mentioned, I think that was the turning point in my life when I took the OR courses at DOMS with GS and CR sir. I almost made up my mind that I should make my career in optimization, and I feel really good that life comes full circle, and I'm now able to say all the way I structured the talk is I'm going to go through different optimization problems I saw across my journey so far, which made me only fall in love more with operations research as time passed. So I thought it would be an interesting journey to see as what the trends are that I could observe across this. So I hope it will be useful for everyone. Okay, I'll just start the presentation. So this is the quick agenda, because I started with Sabre, which is into airline and transportation domain, mainly in pricing and revenue management I got to work on. So I'll cover briefly about optimization problems in the airlines world. Then I moved to Ola, which was more in ride sharing and mobility. And then now I'm with Swiggy, which is more of quick commerce and hyperlocal convenience. So there are these common themes of optimization problems you solve across, just that minor nuances and variations which make it very interesting as you go. So I'll try to just crystallize that into some trends as to how it has come so far and what to anticipate in future is the way we'll go over today. I'll keep the last maybe 15-20 minutes for interaction and Q&A. Right? But if you have a question on the slide, please feel free to just stop me and ask the question. I'm fine with that. Okay. So I'll just start with, because when I was introduced, it was told I'm leading data science. And I just want to start with the definition of data science for myself, right? Very simple definition, which is make data useful for business, right? Now, when we say that, typically when we say data science, people think of AI and generative AI, language models, all of that. But in a simpler form, if you have to think about it, every aspect of data becomes important, right? From being able to collect the right data, having the right data strategy, engineering the data, and creating the architecture in a way where you're able to quickly access the data. It's discoverable for everyone in the organization. Just the data engineering part is super critical. Without that, you can't solve many of the business problems. Then it comes, even before you go and make machines make all the decisions for you, how do you learn the patterns from the data and analytical insights that you provide, so that people can make good decisions in the organization before the machines start making it. And then comes making, building products that are more automated, where machine starts making those decisions. And a lot of people think machine learning is data science, but what does machine learning do? It gives you a lot of predictions, right? What will happen, how will things look, all of that. But somebody has to make a decision on top of those predictions, right? And that's where I think OR and operations research plays a huge role. And that's where it's super important, because I feel this is the yin and yang of making data science useful, where you need both machine learning and optimization to go hand in hand, so that you can make machines function and make those decisions for you. And the last part is the experimentation of multiple models you come up with. How do they perform in real life? Learning from that, iterating, measuring it right. So the basics of statistics and experiment design, all of that become very key. So for me, under the umbrella of data science, each of these aspects are kind of super important. And you can see when I talk through the problems how these things get highlighted. So I'll start with the airline industry. So when we think of airlines, and good thing is across these companies, one aspect that kind of has stayed consistent is you also get to experience it as a customer. Like if it's airlines, you get to travel in the flight. You're using Ola, Uber every day. You're ordering on Swiggy every day. So some of these optimization problems, how they land and how they impact you, you can see it from the other side and kind of then think what's happening in the background, which makes it even more interesting. So when we talk about airlines, right, there are a bunch of business decisions that need to be made, bunch of business problems to solve. Right from the time of what is the schedule that I need to put out there, which means an airline should plan their network, which destinations I'll fly, from where I'll fly, at what time I'll fly, right? And then, of course, you have to price it so that you make the maximum revenue out of the network that you put there, which is pricing and revenue management. Then comes a lot of ancillaries, like how do you merchandise things? You add a meal, you add a preferred seat for extra baggage, multiple things you can unbundle, break down, merchandise it, and kind of sell it as a product to the customer. Then comes the whole operations management of how do you do the crew planning, the roster for the aircrafts. You set up the operations, and like always, things go wrong. So, which means you have to recover from disruption. So each of these aspects have an OR problem behind it that is running and making sure the end passenger is not impacted, right? So each of these has an OR solution. Some of these are long-term, some of these are short-term, right? Like if I talk about network planning and pricing, it's little long-term, because even 300 days out, you need to have a flight there on a certain time and you need to show a price, because people can plan travel pretty early, right? But there are these operations part that we spoke about, or recovery. It only gets more tactical and more real-time when you have to solve these bunch of optimization problems, right? So those are more short-term and tactical problems to solve for. And there are a bunch of inputs that these models need in terms of your predictions of what is my demand going to be when I have multiple itineraries out there. How will the customer make the choice? How will you decide whether I want to fly in the morning or afternoon? And even in afternoon, if there are two itineraries possible, connections possible via different routes, how will the customer choose, right? So a lot of models in customer choice, which are more like logit models, right? And of course, a large scale optimization. If we think of a network like Emirates, it's so big and multiple connections. So on a flight, you will have passengers who want to travel to different destinations on the same flight. So how do you consider all of that and solve each of these problems becomes important, so that at the end of the day, you're building products, you're building solutions so that you can deliver value to the end customer. Right. So that's kind of the overview of the airline optimization problem. I'll go deeper into the pricing and revenue management problem. Right. So when we think of revenue management, what is it ideally, right? You have multiple seats on a flight, and you should be able to sell the right seat to the right customer at the right time, at the right price. So too many rights involved there. So in an economic sense, if we have to think about the problem, I have a demand price elasticity curve, right? I've drawn a straight line, but typically it's a curve. And if you're setting one price on the entire flight, like some of the times we see railways doing, right? You have just one price for the entire cabin. If you're doing that, then you're making some revenue, but that's just a small area under this curve, right? The goal of revenue management is, can I price it? Can I create multiple price points, which could vary in the kind of product you're offering to the customer, which could vary in the time at which you're selling it, and make it more dynamic, so that I can cover the area under this curve even more. The more the area under the curve I cover, the more the revenue I make, right? So that's a fundamental principle for revenue management. So if we have to formulate this as an optimization problem, what do? We create multiple price points. We call them classes, like multiple fares that you have. And all we are doing or trying to solve is to say, how do I break down the capacity I have on a flight cabin into each of these price points? How many seats to sell at 1,000 rupees? How many seats to sell at 2,000 rupees? And that's the optimization problem we are solving, which is, if we have to look at the formulation point of view for it, I'm trying to maximize my price into the traffic I'll get at that price. So out of the total customers who want to travel from point A to point B, how many of them will be willing to pay this price? So it's like little bit of that game theory pushes there. Customers want to minimize the amount that they pay, and airlines want to extract the last price from the customer. So it usually, you can either solve the primal problem or the dual problem. You end up with the same solution in some way, right? So on the customer side, if we look at it, we are solving the dual problem. On the airline side, we are solving the primal problem. And we are maximizing revenue. We have a capacity constraint. We don't have infinite seats. We have only certain number of seats. And I cannot sell more seats than I have demand for at that price point, right? A simple LP, if we think of it, right? When I solve the dual of this problem, what we get is the shadow price of every seat. That is, what's the minimum you need to charge to be optimal at this point. That's a very important insight, because what it enables is, let's take a flight from Bangalore to Dubai, right? On Emirates. Now on Bangalore to Dubai, I have multiple people, some who want to travel to Dubai, some who want to take a connection and travel to Amsterdam, some who want to travel to US, multiple destinations. Now, how will I set the price for all of them? Imagine just the explosion of the space or the dimensions of variables I need to have if I start doing that. But if I have a shadow price based on all the demand of all the flights that I have, then I'm able to come up with, the minimum price I have to charge on every flight, every seat, so that whatever connection you're taking, I have the minimum price for that entire route, right? So that's how a lot of these network problems are solved, where you solve the dual of the problem. But if you have a point-to-point carrier, like an Indigo, with mostly traveling only point to point, where you need not think too much about connections, there I can get more nuanced, more sophisticated, and I can break that down into a multi-stage decision-making problem, like a dynamic programming problem. Just one check in between. I'm getting little technical. I hope it's okay with the audience, or should I keep the technicality level higher, lower? Any feedback there?
I'm very happy with the
Yeah,
technical.
it's good.
Okay. Okay. Good. Okay. So we can formulate it as a dynamic programming problem, where the multiple stages we have is different capacity remaining on the flight. So when I have 100 seats, it's not filled yet, I can set a certain price, and I have an upcoming demand in the future time periods from now until departure. Typically a flight starts selling 300 days to departure. So on every day I have to set a price. So almost I have so many time horizons I can look at, and I have multiple seats that we can sell on each day. So it kind of gives a good setup for a dynamic programming problem, where you're looking at these state transitions. If I sell one seat, then I'll go from, this C equal to 1 capacity to C is equal to 0. I'll make a certain revenue, and I will move to tomorrow, which is I'll move to T2, which is the next time period. But if I do not sell, I carry the same capacity and move to the next time horizon. So this can be done, and this is done on a lot of point-to-point carriers, but it gets too large scale and unsolvable when you think of big network carriers who have multiple connections, multiple destinations. So both of these methods are applied in bits and pieces there, right? Then I'll come to mobility, which is the ride-hailing scenario. So when we think of ride-hailing, all of us have experienced it as customers. There are multiple optimization problems you need to solve for, right? So you have search pricing, which is trying to match the demand and supply and try to hit that point where demand is equal to supply. So if I have more demand than supply, I'll try to keep increasing the price in such a way that I can clear the supply at a certain point, right? So that's an optimization problem we solve for. But of course, there are constraints. There are regulation constraints that you cannot, really charge higher than a certain amount. And there are some profitability constraints that you cannot solve below certain amount. So there is a range of operation, and within that range, we are trying to find the optimal sweet spot. Right? Then you have pooled rides, which is like the shared cabs where multiple people travel on the same cab along different. There'll be some overlap in their routes, and you kind of have to match the riders who should match with whom. I'll get a little deeper into that problem, which is a very interesting one. Then there is a problem of which cab with which customer, right? Matching the rider, and it's a typical assignment problem that we learn in our courses. And I could see that real application, Hungarian, all of that working. And that's a typical bipartite matching problem between the rider and the driver. Then there is thing of incentive design, which is when you have to bring supply on ground, you have to get more drivers on ground, you have to design the incentives in such a way that they come to the platform, they give you a certain number of login hours, and they stay till your peak periods end. So how do you design the incentives? It could be on the number of rides you do, it could be on the amount of time you spend on the platform. How do you design that so that you get the maximum response from the supply side? Then there is supply planning, which is more, it ties into incentive design, but also about how much supply we should get at what time and what space. So it's a spatio-temporal problem a bit, where we need to understand the patterns of demand. Where does the demand originate? Where does the demand want to go? Where should we position the cabs? Like when you start in the morning, how many people should we make login at every time of the day? Because there are off-peak periods, there are peak periods. So how do you do the supply planning for it? So multiple optimization problems. So we can look at the matching pool rides one more closely, right? So share or a pool ride is one where you have multiple customers and you come and say, I want to ride a shared ride. Now you have to match that customer to another customer who is already on a ride so that your routes are having some kind of overlap. You both want to go at the same time to a certain same place. But why do people want to go on shared rides? Because it's cheaper, because you can take money from multiple customers, but driver is only driving so many kilometers. So it's a more profitable, it's more environment friendly for us to do this. So shared ride as a use case is a very strong use case in mobility, right? Now, how do we solve this problem? If we think of it, at every instant, there are so many customers who will come on the app and say, I want to ride, right? And so many customers who are already on a ride. Now, just the number of combinations you have to look at to say who to match with whom, that combinatorial optimization problem is a high scale problem, right? And customers won't have that patience to wait forever, which means you have to really solve it with low latency and go back to the customer to say, you got this right? You have a few seconds, not even seconds, sometimes milliseconds to solve the problem. Right? So when we thought about this problem, one idea was about how can we break down this problem into something we can pre-compute as much as possible, so that in real time when the customer is asking, it becomes a very quick, greedy solution that we can come up with. Right? So one thing that was done here is think of this like a graph where there are certain number of customers who are already on a ride. This could be an individual customer or two customers who are already on a cab, because typically a shared ride can have up to 3 passengers, right? So there are then a set of new requests or new customers who want to book the ride. And when the request comes, now you can have all the combinations possible. You can match these new requests with any of these existing customers who are on a ride. This becomes a nice clique detection problem, right? Because imagine this as a graph and the score on the edges being a function of the overlap they have in their route, the deviation time the customers are going to face from their direct route, how much time it takes to travel, and the revenue you're going to make, how profitable the route is. More the overlap, more profitable the route is, right? As a function of all these, this can become a problem of finding cliques. And we can take a bunch of origin destinations and solve this problem in a batch mode, in more parallelized versions of it, and pre-compute some of these scores and keep between different origin destination pairs. Once we have that, in real time when requests come, then it's a more like a greedy matching problem where you have a score between every new request and every existing ride, and then you're trying to match it, right? So that's how we kind of solve the ride share matching problem. Then I'll come to quick commerce. I think COVID time is when everybody kind of took over to quick commerce because we couldn't get out of our houses and we needed everything coming home. Now it's everything in minutes, less than 10 minutes, 8 minutes, 7 minutes. It's getting crazier day by day, right? It has changed the habit of many folks where maybe we start cooking and then we look for ingredients on the app. So that's how world is changing. So for this, it means that the stores where you are having all of this inventory, it needs to get closer and closer to the customer, right? If quick commerce is a reality, right? That means network design, or what we study as facility location problem, is one of the important first strategic problems to solve for when you look at quick commerce. Where to locate your stores so that we are accounting for the coverage of different customer cohorts and pockets that we have. We are looking at how the competition is, because more the competition, the demand gets kind of split across multiple competitors. So where are the competition locations? Where should you strategically place your set of stores? And what's the cost structure? Because operating each of these stores has a lot. First of all, setting up these stores has a bunch of fixed cost. Then operating has certain operating costs. Now, if you have to really break even, that means the amount of demand density that you need to hit has to be at a certain level. So all of these kind of become constraints for us to really come up with this network design of where to locate the stores where you have this inventory so that you are closest to the customer and deliver the kind of speed that we want to deliver. Then the next part is, okay, you created these stores. Now the assignment part that we were discussing, right, which is like a bipartite matching problem, where you have an order that has come in and you have multiple delivery partners around. How do you assign the order to them? So this is very interesting, especially in food delivery, because typically in all other deliveries, you will start immediately looking and it becomes a simple assignment problem. But when it involves food, there is a certain amount of preparation time involved, which means there is a sweet spot you need to hit in terms of when should the delivery partner reach the restaurant. Because if you reach too early, you're wasting delivery partner's time. They're staying idle waiting there. If you reach too late, the food is waiting for the delivery partner. So it's really a just in time and as much hit the sweet spot as possible assignment problem. And when we do this, it's a high scale problem, especially in a scenario, if you take food delivery case, the number of combinations you are evaluating is almost like more than 4 million combinations in a minute you will be evaluating. That much demand has gotten aggregated. And each of these needs some prediction. You need a prediction on how long will it take to prepare the food. You need a prediction on the travel time. How long will it take for the driver to travel the first mile, the last mile? what's the probability that someone will cancel, right? So a lot of these predictions, which means you're evaluating more than 1 million predictions even to make this decision at every minute, right? So super interesting problem to solve. And when we assign delivery partners, you'll get the delivery partner quickly when you plan the supply well, right? So supply planning is a problem that I think every strong operations or like every core logistic, any company which has very core logistic operations problem needs to solve for, which is the supply planning or the staff planning in some way, because there also it's a sweet spot problem, right? You need that perfect balance. If you plan lesser supply, there are lost deliveries, lost demand. You're not able to serve the potential of the demand we have. But if you want to serve the potential of the demand we have and you try to have enough supply, the demand is variable. It's not a flat demand curve. So there are peaks, there are off peaks. So if you have to plan the supply to that level, it creates a lot of idleness and lack of utilization of the supply side, right? So it's again a sweet spot problem. And how do you plan it out in such a way that you try to trace the demand curve as closely as possible with the supply, right? So almost you have to create those slots of, half an hour, 1 hour, how many people will you call in at that particular slot based on the demand that we have, based on, the time it takes to deliver an order. Like sometimes it takes half an hour, sometimes it takes 1 hour, depending on the type of the order pattern, the traffic situations. So each hour is very different from that angle. There are cancellation behaviors from the customer side. There is also show up behavior from the supply side, right? So we have to account for all of these inputs, be able to predict, behaviors, predict demand forecasts, use all of these forecasts and solve the optimization with the decision variable of how many people we need to have at what time, so that our system is operating at maximum efficiency possible, good utilization, and for the customer also it's a good experience. So it's a very thin rope to walk on, and sometimes we get into that multi-objective optimization situation where you want everything to happen, but none of it is happening well, right? So how do you design those trade-offs? How do you solve this multi-objective problem is an interesting thing we came across in supply planning. Then the last part is we spoke about the assignment problem, right? But it's not always like one partner has to assign only one, we assign only one order. That's the typical assignment problem. But you are in situations where, because you could plan the supply only a certain way to cater to the demand that you have, same supply has to cater to multiple demand requests, which means the same delivery partner has to deliver multiple orders, right? So now this just increases the combinatorial space we were in earlier. It was just delivery partners and orders. Now you have order, cross order and delivery partners, right? So huge problem. It's a vehicle routing problem if we think about it. It's a capacitated vehicle routing problem with time windows, right? So there are a bunch of constraints here and objectives to solve for. So objective is more like you have to minimize the cost of delivery. It is a function of distance and time of the delivery partner's end. And then you have to deliver the best customer experience. You have promised a certain SLA and you cannot not meet that. And you also have to meet the expectations of the delivery partner, that you're not remaining idle for a long time, you're utilized well, which means your earnings and utilization are correlated, which means you have to meet the earning goals of the drivers, right? So typical problem marketplaces face in catering to both demand and supply side of goals or objectives. Then there are constraints in terms of the weight and volume that you're carrying. And sometimes you might also have last in, first out, especially if you're stuffing in things into a three-wheeler and you have to place it in a way where, the very delicate ones or perishable orders, they go out first and they can't kind of, remain there, they'll get spoiled. Then there are promised time windows, which are constraints. And you can pick up order only after all the orders get packed, right? So multiple constraints like this. It's a high scale problem and tough to solve. So one of the hacks was, can we break it down into two parts, right? One part was about, we'll just optimize for the last mile. We'll not care about which delivery partner is going to deliver it. First, let's try to find good candidates of orders who can be delivered together, where their last mile has a lot of overlap from the depot or from the store, right? So we solved the last mile problem for a scheduled delivery because you get the orders much ahead of time, so that you can solve more easily as a last mile optimization problem. Then we select the good batches of orders that can go together, and then solve the first mile optimization as an assignment problem, right? So this helped us strike a balance, and we could do this iteratively as well. As more delivery partners show up, you keep running these crons in an interleaved manner, and that helps you kind of achieve both the goals that you have for both sides, right? So these are some of the problems. I know I briefly kind of glanced through it, didn't go into too many details, but I hope it gives an overview of how we are solving that. So I would like to cover a little bit of trends across this journey observed, right? So if we think about it, when we were in the airline side of domain, we had 300 days to solve, and every problem could be solved like a batch optimization problem. So not a lot of focus was required on speed of achieving the solution, right? How do you keep optimizing the solver itself, right? So that was not a huge focus. But when we think about it, most of the things are going on demand. People are getting very instant gratification focused, which means running more real-time on-demand optimization is becoming more and more important, where you don't even have 300 milliseconds to solve the problem, right? So that's one definite trend. The second is a lot of things, just because of the flurry of B2C domain in itself and more companies directly reaching out to the customers, everything is kind of becoming small scale to large scale problems to solve for, right? What that also means is the real value scientist is bringing in is also how to break the large problem into smaller problems to solve. The decomposition angle becomes more and more important as to how are you able to break down a big problem into smaller problems that can be solved, not losing on the optimality for the global problem, right? That becomes a kind of a key focus area. Then a lot of inputs into optimization, which used to earlier come from a lot of traditional time series models, or we have these exponential smoothing, ARIMA models, Kalman filter, multiple of those were used earlier. Now, majority of the inputs are coming from, deep learning models, generative models. So the kind of integrations you need to build to get the right inputs into the optimization is getting more and more nuanced. And in most companies, everybody wants everything, which means all the problems are pretty much multi-objective problems. So how to handle that multi-objective problem, understand the multi-criteria decision making, and educating each stakeholder on that and frameworks around that is more crucial than solving the problem itself. Because sometimes due to lack of clarity on what are those multiple objectives and how do you handle it, you face a lot of problems downline. So it's better to upfront clarify multiple objectives. How will they trade off? How will we model it? That becomes a key area to focus on. Then from exact algorithms, we have moved towards more heuristic approaches, smart approaches that solve 80 to 85% of the problem, right? And only in really high scale problems where even that plus 1% means a lot is where a lot of sophistication and more rigorous techniques to solve the problem are applied. In most cases, you start off a version 0, version 1 with more heuristic solutions. A lot of solutions are experimentation driven, simulation driven. So when someone has ideas, they'll have like 10 ideas, right? So almost all the companies I have worked with had a simulator in-house built, so that you can evaluate 10 ideas, because everything you cannot take to production and experiment live. It takes a lot of effort. So simulator plays that role where you can experiment on simulator 10 ideas and probably 3 will make it to production, so that you can observe the experimentation live and draw the conclusions. But simulation capabilities and building almost that shadow system of your actual business is an area which is very key for many of these optimization problems. Of course, majority have some commercial solvers to solve it at large scale. So a data scientist contribution becomes lesser about how do I solve, than it is actually more about how do I simulate, how do I model the business problem itself and translate the business problem from English to that mathematical model. That is the key skill more and more that is being looked for or becoming important for people to solve the problems, right? So yeah, that was the major part I had. I hope it was useful. So I would like to spend more time on questions and interactions.
Thank you very much, Goda. It was a great presentation. And questions from the audience? Okay. So then let me start off a question, and hopefully people will also manage to write their questions down and ask. So Goda, one of the questions that I have written down is, in many of these optimization goals, sustainability is really not a parameter, right? So environmental sustainability is really not. In particular, especially when you try to batch requests and deliver, there is more a commercial goal. Of course, there's a small side goal of ensuring the vehicle is used to capacity. So is it possible for to actually incentivize people to make their demands significantly earlier, right? So that deliveries can be batched and bunched together, right? So, for example, you gave this thing saying that people start cooking and then decide what they want, right? Is it possible to kind of incentivize people not to do that, but to actually plan that I'm going to make this dish tonight or tomorrow night or something like that, and then place the order?
Yeah, I think it's a great question, right? So, couple of things there, right? One is coming more from when you're trying to make your system efficient. Is it so sustainability and cost almost going hand in hand, right? So even if you're optimizing for the cost, you're ending up routing it more sustainable. They are not at loggerheads with each other, but there's a demand shaping side of it, which is how do you shape the customer's behavior towards sustainability more? So recently, I don't know if it's launched in Chennai yet. So there is a new product, for example, Swiggy has launched, right? When you're ordering, we say that, are you okay kind of waiting for 10 more minutes, right? You like it's called like I don't have rush, no rush, right? Come aram se kind of thing, where it will help us, batch your orders and it will lead to greener earth, right? So there is a product that was launched. It saw a decent adoption and appreciation from the customers, but even from the customer's angle, I feel that cost benefit, if you're sharing it with the customer, then there is more of that, adoption and the behavior change. Only doing it for sustainability, you really need enlightened customers kind of adopt it. If you want mass adoption, I think it should definitely come from cost saving, sharing that cost saving with the customer as well, so that you can drive that kind of demand shaping. So we are going to also experiment the pre-order part that you spoke about. It's in the pipeline, which is, can we tell, like, you can order much ahead of time, plan your dinner, plan your lunch, right? So that it helps you batch, it helps us also build more predictability in the demand so that you can plan better for it. It has multiple benefits. But sadly also, entire market is moving towards more instant gratification. It's my personal opinion.
No, that's also because I guess there is a very young generation that's probably very large part of the population. They are attempting to actually learn their ropes with things like cooking and so on and so forth. So that's the place where I guess there is also a lot of revenue, but there's also a lot of instant gratification, so to speak. So
I
I
think
think
there is
there is,
a mix of customers who are convenience seeking as well as price benefit seeking. It's that
yeah,
combination.
yeah. So and others, do you have questions?
Please open up. No need to. No
Yeah,
question is a bad question.
yeah. Priyam, you can speak into your mic, or let me just read it for Priyam. Yeah, sure. Okay, so what Priyam asks, Goda, I'm sure you do. I just read it for everybody
No,
else.
yeah, I'm able to see it on the.
Yeah. What are your views on important techniques for solving large problems, maintaining low gap?
Yeah, like I said, for example, it is mostly in breaking down the problem. Just to give an example, let's take a city, right? And you're trying to optimize which orders to give which delivery partners, right? There is no right way to break it down. You will have to optimize the entire city together because let's say there's a restaurant here and there's a customer here. Now, the delivery partner who is around the restaurant can also deliver on the other side of the restaurant, which means it's almost a circle around the restaurant. All customers need to be optimized together, right? So you can't really break it down theoretically if you speak about it. But based on the data patterns, you can come up. We also have a blog about it on the Swiggy blog site, right? How can you break down, for example, this city into clusters, which actually interact lesser with each other in sharing supply, right? Now, if you're able to identify those, then with minimal optimality gap, you can break down a city level problem to cluster level problem and solve the same problem in a smaller cluster. Right. So one way is to how do you break down the space of the problem itself into clusters which are not tightly interacting with each other is one way. The other way of breaking down the problem is more hierarchical, where you have a strategic decision you're making. There's a tactical, like in the facility layout problem that we discussed. Strategic decision of where to locate, and there's a tactical decision of who is serving which customer, right? You can do it a lot iteratively where you solve the bigger problem, find a solution with demand distribution, then go back and edit more like the decomposition approaches that we know. That's another way to break down the problem.
Thank you, ma'am. Sir, may I ask one more question?
Yeah, please, please. This is for you
More
guys.
questions, I'm happier. It means people were listening.
Thank you. And just to just a brief idea that you got, it's more of a decomposition or make using smart heuristic as you mentioned. So there are other large scale techniques that we usually read in papers also, like column generation and other exact techniques. So are they really being used in the industry, or are they most restricted to the research papers, and or
No, no.
are they usually
For
using?
example, I did see they are used. It's not like they're not used. For example, in the airline problem that I was talking about, our solution when we had to work on the aircraft routing problem,
Yes,
which aircraft goes to which airport and from there to where, etc. Right? Column generation was used there, right? But in a lot of real-time optimization approaches, there are certain there are no guarantees of convergence you can provide, and you do face some challenges there. Uh, when you go into more real-time or more urgent problems that you're solving for, it's usually the heuristics on good neighborhood searches that you can do. That is more relied on in more real-time niche problems.
so
Right?
you are
But both are
suggesting.
used in the industry depending on how much time you have to come up with the decision.
And so, ma'am, you are suggesting instead of these specific algorithms, like more of a math heuristics is kind of being implemented.
It's a proper algorithm as well. For example, if I have to talk about neighborhood searches, right? In order to come up with the right neighborhood to search in, you might solve a small graph optimization problem. Right?
Yes,
So
correct.
it's about breaking the big optimization problem into small optimization problems, which are themselves theoretically backed optimization and not heuristics.
Thank you so much, ma'am. That's what's.
Other questions from the audience? Pradyumna, you have a question. Please go ahead.
Yeah, I have one. So you can hear me, right?
Yes.
Yeah, very clearly. Please go ahead.
Yeah, I have one question. Like, so does the language in which the algorithm is coded have an impact on how quickly the decision is given? Like, what technology is used to code the algorithms? So does it
Uh,
have an
See,
impact?
most of the data science teams I have seen using Python based solutions, right? Whereas when we have to put certain things in production, I've also seen uh, when you use commercial solvers, it does not matter a lot because they almost have interfacing across different languages. But the key core thing is happening via the same solver, so it does not matter. But when you're trying to build your own optimization or heuristics, typically I've seen data scientists do it in Python. Many of them are productionizable. There are a lot of open source solvers also, like OR tools, that's used. Um, in some cases, I've seen where really millisecond latency, it goes to engineering team from data scientists, and they are more, they code up things in Java and then or Go sometimes. So those are the frameworks used.
Thanks for the question,
Thank you.
Pradyumna. Are there other questions from the audience?
Yes.
Yeah, please go
So,
ahead.
yeah. So my question is that regarding you talked about the facility location problem, right? So is there any competition cooperation kind of facility location where the facility is being shared by more than one partner, maybe Swiggy, Instamart, and Zepto sharing a facility in sort of a remote location where there are less number of demand or something? Is that possible, or do you see a
So
possibility of that?
at least across competition, though, there is no sharing of data or no planning together, right? I think that's not even promoted. I think because it it has other regulatory constraints. But where this kind of a thing happen is where you are a super app, right? For example, if you take a Grab or a Gojek or even Swiggy for that
Okay.
instance, right? You have multiple businesses, right? You have grocery as well, you have mall as well, which is more for electronics and stuff like that. And you have some other business. Now we are sharing the delivery partners anyway. Now you can share capacity locations or fulfillment locations as well across business categories of the same company. That can happen.
Okay. Thank you.
Let's say you have an idea based on data you have presented. How do you convert that idea and try implementing? Okay, good, great question. Uh, See, if you have an idea base, so at least as students, I would say when somebody wants to become a future data scientist, there are certain, you know, open source data sets people pick either from, Kaggle, there is some global supply chain data. I'm sure you all being from academic, you will be more well versed with open data sources than me, right? Uh, but there are also problems you can solve without data as well. What I meant by that was, like I have seen many blogs people have written, like during COVID, especially when this was happening, right? Somebody came up with an optimizer. How should you distribute vaccines, for example, right? You can take a public problem that's out there, right? Use whatever public data sources are possible and try to uh, solve a problem. What is key in productionization is, are you able to take a business problem, translate it into a math problem, build the right suitable formulation that gets solved fast? That's the first part. Second part is the change management and maintenance part of it, which is once something is live and in production, how do you build tracking systems so that you're able to see where it's working, where it's not working? When it's not working, how do you quickly find the root cause? How do you iterate and change it and put it to production again? These are the aspects which are different when it comes to productionization. But the core part of formulation, being able to code up the solution, try it out, that remains the same whether you do it on public data or not. So I would focus on formulation skills so that you know which mathematical model or way of solving applies where. And then we are very conscious about tracking, maintaining, doing the change management part for a good future data scientist.
Other questions from the audience?
Hello, ma'am. I'm audible?
Yeah, Goda, I have a question. May I ask a question?
Yeah, please
Goda,
go
can you hear
ahead.
me?
Please, yes.
Yeah.
Yes, sir.
See, do you have principles of cross-docking that is being applied in Swiggy? That means a set of orders are picked up by a person, and then at some place, and delivers. You have
Yeah,
such.
we called it a we called it a relay model somewhere, right? You do in relay races. One person is
Yeah.
giving it to other.
Yeah.
The generic business as usual model. But for example, during COVID, there were certain containment zones which were created, right? Now, if somebody inside the containment zone has to get an order delivered, then from a restaurant which is outside the containment zone, then we had to use this kind of a model where a delivery partner picks from the restaurant, comes to the border of the containment zone, hands it over to another delivery partner.
Yeah. Yeah,
So that's
correct.
the
I
only
understand.
use I have come across. But typically, we are able to manage within the supply within a certain zone. So this cross docking doesn't.
Okay. Thank you.
Thank you, sir. Tulsi, you had a
Yeah.
question.
Yeah, hello, ma'am. Thanks for this session. So I had a question regarding like how actually you solve a problem. So let's say like a quality, like how you solve a problem, it's proportional to the time you spend on that problem. Let's say you have a proper R&D team versus a in-house engineering team, so that a problem comes and you have to solve it immediately. So let's say you see in a lot of like MS or PhD papers and all in the research works for a problem, they take a lot of time like to completely analyze and solve a problem, and those formulations are really complicated and slightly difficult to implement. So in real life, like what is your way to tackle the problems? Like, do you have a instant in-house solutions by the engineers with not so complicated models, versus you prefer a proper analyzed predefined solutions and add on to that? Yeah.
I'll answer it in 2-3 parts, right? I think typically in a business scenario, or even in business, I think differentiate a company like Swiggy, which is more startup-ish, versus let's say when I was working in Sabre, which was more like big companies who have budgets to have an R&D team, do research, right? It is different across companies, right? So if you are a company who has an R&D team, there these kind of things used to happen where the primary responsibility of the R&D team is publishing work and looking at the things with more theoretical approaches, trying out fundamental solutions. Whereas if you take more startup-ish environment, there solving the business problem is core. So you will always start off with version 0, or what you call, where you might just put a greedy approach, right? So that you solve 60% of the problem. Now it goes through an evolution. As you go through V1, V2, V3, you get more and more, you have to get more and more sophisticated so that you keep solving for bigger and bigger chunks, right? And Swiggy being where it is right now, I would say we are already in the V2 or V3 area, not the V0, because V0 is typically when you are a very young company, right? So now it's in the phase where you have to solve a problem, you have to think of more involved solutions, which might become, you have to refer research papers. You might not, and you also like some work is also published by Swiggy team, not of course very like theoretically research, but more applied research papers. So I would say it's dependent on the problem and the evolution that problem has gone through at the company. If it's at a state where it's evolved and any change you have to bring in needs to solve a more complex problem, it does have to go through that. So you have problems you solve in 2 weeks, you have problems you take 3 months to solve. Both exist.
Yeah. Got it. Thank you so much.
Lovely to hear all the questions. Sir, you're on mute.
Okay. Yeah, thanks everyone for the great questions. Goda, I have one last question. Especially with ride sharing, are you aware of social networks of ride sharers that have been set up?
Social networks of ride sharers. More from just interacting with each other point of view? Or
No, I mean a system. Has anybody attempted to set up a system where, for example, if I do ride sharing with a person, and I have a thumbs up or thumbs down without violating privacy, right? So you see this, right? Let's say I
So
shouldn't
there
ideally
was,
know.
yeah, I understood what you're saying. So we did
Yeah.
attempt it when we were in Ola. We had called it Ola Social or something like that, right? So basically, like if you are liking a co-rider, and you said you had a good experience, and you get another chance to match with the same person, will you give it preference? Is one thing we had tried. But I've also seen a lot of carpooling apps where the rider who is offering the ride is also a normal customer working at the same tech park, and you open up your ride and say, I'm going to office tomorrow. And so there are companies who are doing this carpooling kind of app where that social network does exist, that you have set of people you want to match with, and there that happens, but it's not very text heavy that you're chatting with each other, you're sharing posts. That doesn't happen.
Yeah,
It's
that's
more
not what
in
I
the
meant.
context
Actually,
of sharing rights. Yes.
yeah, without violating privacy. That was a question. Thumbs up, thumbs down, and I shouldn't know who the name of the passenger is. And but the next time somebody else wants to take a shared ride, a person who lots of people give thumbs down is possibly a person who shouldn't be shared a ride with.
It was an
Just-
experiment pilot that we had tried. I don't think it was scale.
Okay, very interesting. Okay. Yeah, thank you very much.
Thank you so much.
Thank you very much, Goda. So I guess we'll bring this great talk to an end now. And thank you very much. Please do visit us. So we have this nice center that's been set up at the institute. This is funded by FedEx. It's on sustainable and smart supply chains, which is right up your alley, right? And I'm sure you visiting us will make us better. Give us
Sure,
greater
sir. I'll plan for
experience.
this. I'll plan for it.
Yeah. Thank you very much. I think Professor Rajendran had to drop out. He's traveling.
Yeah.
I'm sure he would have been happy to thank you too.
Sure.
On behalf of everyone, thank you very much.
Yeah, thank you.
Thanks, everyone. Please stay tuned for our next set of talks. We will track our social media channels and we will let you know. Thank you for attending.
Thank you.
Thank you. I'm stopping record. Thank you all.